Hey everyone. Last video we saw how the ideal gas law allows us to make sense of why the heat capacity at constant volume and the heat capacity at constant pressure are different for a gas. Now we need to start thinking a little bit more about all the different quantities that we know about for a gas. There are four main ones. The pressure of the gas, which just tells us how much it's pressing against its container. The volume of the gas, which just says how much space the gas is taking up. The number of moles of the gas, which tells us, well, the number of moles. And the temperature of the gas, which allows us to find out how much thermal energy the gas has if we have some other information. These four quantities are related together by the ideal gas law, which just says that the pressure times the volume of a gas is equal to the number of moles of the gas times the ideal gas constant R times the temperature. Now, the problem here is that there are sort of a lot of quantities in this equation. There are four of them that are going to be different for every single system that we study. It can be hard to think about all of this just numerically. And so in this video, we're going to introduce some tools that we can use to better understand what's happening during processes. There's two of them that we'll see in this course. They're called pressure volume diagrams, or PV diagrams, and internal energy versus temperature diagrams, or UT diagrams. These graphs are more or less just what they sound like. A pressure volume diagram is just a graph that has pressure on one of the axes and volume on the other one of the axes. A UT diagram is just a graph with internal energy on one axis and temperature on the other axis. But why a pressure volume diagram? Why not a pressure temperature diagram, or for that matter, a volume temperature diagram? Well, there's a specific reason, and that reason has to do with work. We know that the work done by a gas as it changes its volume is equal to the negative pressure times the change in volume if the pressure is constant, or an integral if the pressure is not constant. But crucially, it only depends on the pressure and the volume of the gas. It doesn't depend on any of the other quantities. Again, you may not remember your calculus super well, and that's fine, but you probably heard that the integral of a function is equal to the area under a line if we graph that function. That's true here too. If we make a graph with volume on the horizontal axis and pressure on the vertical axis, then the area under that line in the graph will be equal to the work done by the gas as it expands or contracts. One of the reasons this is so useful is it actually allows us to calculate work for systems where the pressure is not constant. As long as the shape of the graph on a pressure volume diagram is a nice geometrical shape that we can calculate the area of, we don't really care whether the pressure or volume is constant. We just need to calculate that area and we know the amount of work done. But there's actually another reason why pressure and volume are interesting. Think back to the ideal gas law. The ideal gas law relates pressure and volume with the number of moles that a particle has and their temperature. You can use the pressure and volume from a PV diagram and immediately relate it to the temperature of the gas just by knowing the number of moles. If you know the temperature of a gas and the number of moles, you can determine the total thermal energy of the gas, assuming you know the number of modes that each of those particles has. Now, I know this is a little bit hard to think about in the abstract, so let's take a moment and actually look at an example of a pressure volume diagram and how we can use it. So here's an example of a problem that we might see. We have a pressure volume diagram for 1 mole of a monatomic ideal gas. We want to know three things. We want to know the change in internal energy, the heat, and the work. With pressure volume diagrams, work is always the easiest. We can just find it by looking at the area under the line. In this case, that's everything between these two red dotted lines and below the purple line. Now, this geometric shape that we're looking at is a trapezoid, but you don't need to know what a trapezoid is. Instead, let's just break it into two pieces: a rectangle and a triangle. The area of a rectangle is just its width times its height. The width of this rectangle is 4 times 10 to the negative 3 meters cubed. We have to be careful about our units here. It tells us that the volumes are in units of 10 to the negative 3 meters cubed. And the gas is expanding from 2 to 6. So our width is 4 times 10 to the negative 3 meters cubed. And what about our height? Well, it's marked right here. The height is 20. But 20 what? Well, it's in kilopascals. We don't really need to know what a Pascal is. It's just the unit that we use in this course to measure pressure. Kilopascal is just 1,000 pascals, as a kilogram is 1,000 grams, and a kilometer is 1,000 meters. So the height of this rectangle is 20 times. So the height of our rectangle is 20,000 pascals. And what about our triangle? Well, the area of a triangle is 1/2 times the triangle's width times the triangle's height. The width of the triangle is exactly the same as the width of the rectangle. The height of the triangle is just this distance here. This turns out to also be 20,000 pascals. It goes from 20,000 pascals up to 40,000 pascals. The difference between those two numbers is 20,000 pascals. If we plug these numbers in, we get 80 for the rectangle and 40 for the triangle. Just so you know, a Pascal times a cubic meter is equal to a joule. And so the total amount of work done is just these two numbers added up, 120 joules, right? It's actually not. The number is correct, but the sign is incorrect. The volume of this gas is increasing, as indicated by this arrow. The arrow is pointing up and to the right. To the right on this diagram is towards increasing volume. If the volume of a gas is increasing, the work done by it is always negative. It will be up to you to remember which is which, but again, it's really simple. If volume is increasing, work is negative. If volume is decreasing, work is positive. So now let's think about delta U. You might say, well, we don't know delta U, and you'd be right, but we actually have all the information that we need to calculate it. We have pressure and volume at our initial and final states, and we know how many moles we have. It's just one. From this information, we can calculate a change in temperature. And because we know that this is a monatomic gas, we can use the change in temperature to calculate the change in thermal energy just by looking at how many modes the substance has. So we have all the information that we need to calculate the temperature at the initial and the final states. All we have to do is plug these numbers into this equation and solve for temperature. When I plug these numbers in, I get that the initial temperature is 4.8 Kelvin and the final temperature is 28.9 Kelvin. Now, a key thing to note here is that the ideal gas law always works in Kelvin. In the past, we talked about changes in temperature, and it didn't matter if we used Celsius or Kelvin. But when we're talking about the actual temperature, like we are in this case, then you're going to be using Kelvin. So our change in temperature is just 24.1 Kelvin. If we want to know the change in internal energy of the gas, which is just the change in thermal energy, we just need to calculate the heat capacity and multiply by the change in temperature. We know what the heat capacity of a gas is. It's equal to 1/2 times the number of moles times R times the number of modes per particle. Because this is a monatomic gas, the number of modes per particle is 3. The number of moles is just 1, and so our equation becomes C for this particular gas equal to 1/2 times 1 times the ideal gas constant R, which is 8.314, times the number of modes per particle, which for a monatomic gas is 3. We know that the change in thermal energy is just equal to the total heat capacity C times the change in temperature, and this is equal to 1/2 times 3 times 8.314 joules per Kelvin, because that is the units of the ideal gas constant, times the change in temperature, which we just calculated is 24.1 Kelvin. When I plug all these numbers in, I get that the change in the thermal energy for the gas is just equal to 300.6 joules. And because this is a gas, thermal energy is the only kind of energy that it has. So this is also equal to delta U. The last thing we'd want to calculate is Q, the heat that goes into or out of the gas during the process. Q is not a state function, so how can we compute it if we only know things about the state of the gas? Well, we can because of the basic equation of thermodynamics. It just says that delta U is equal to Q plus W. We've already calculated delta U and W for this case, so we can just solve for Q. And so, to summarize, as our gas expands, it does negative 120 joules of work. It changes its temperature by 24 degrees, which means that its total change in thermal energy is 300.6 degrees. And during the process, it takes in 420.6 joules of heat from its surroundings. Now, you're going to get lots of practice with these kinds of things, both in DL and in practice problems. But again, the key thing to take away is that a pressure volume diagram actually gives us a ton of information about what the gas is doing. We can calculate the work done by the gas directly from the pressure volume diagram just by looking at the area under the line. This is true even if the pressure is not constant. If the pressure is constant, of course, we can use the much simpler equation work is equal to negative pressure times the change in volume. The pressure volume diagram can actually also tell us what the temperature of the gas is, so long as we know the number of moles of the gas. This is true because, for the most part, when we're looking at pressure volume diagrams, we're talking about an ideal gas, a gas that behaves according to the ideal gas law. The temperature just depends directly on the pressure, volume, and number of moles, so we can compute it directly. If we can calculate a change in temperature and we know the specific heat or heat capacity of the gas, we can then immediately calculate the change in thermal energy. We may need to compute the heat capacity by knowing the number of moles and figuring out how many modes each particle has, but we know how to do that. And once we have that piece of information and the change in temperature, we can directly compute the change in internal energy. And once we know the change in internal energy of the gas, as well as the work that is done on or by the gas during the process, then we can immediately compute the heat just by using the basic equation of thermodynamics, delta U is equal to Q plus W. This starts to show us why pressure volume diagrams are so useful. Pressure volume diagrams contain a ton of information, not just about the process, but about the gas itself and how it's behaving. Of course, a lot of this did rest on us knowing that the gas was an ideal one, but usually that's going to be the case. Even if a gas is not perfectly ideal, it's still going to be usually okay to approximate it as an ideal gas. There's one other key concept that we need in the model of thermodynamics before we can sort of finish out the course. But to get there, we have to take a little detour into thinking about probability. This is going to feel a little weird at first, like, why are we doing this? But I promise you, we'll figure it out in the long run. And we'll start talking about that in the next video.